In this section the following subjects will be covered. Identification of common components and the location on the hydraulic schematics. Providing an overview of the operation of each individual function, while relating to the flow paths, and components used, for these functions. It promotes use of the Genie service manuals, and schematics, while making adjustments or troubleshooting hydraulic circuits. 2 function manifolds are used on DC scissors products. 1 function manifold is used on the GS 1530, 1532, 1930 and 1932. Other larger models including GS 2032, 2632, 3232, 2046, 2646, 3246 and 4047 use a similar function manifold, with the addition of a solenoid-operated valve used to switch between low and high drive modes. Both manifolds are responsible for functional control of lift, drive and steer functions. All machines are equipped with a manual brake release manifold. GS 3232 models have an additional manifold, responsible for functional control of outrigger extend and retract. GS 3232 outrigger cylinders are equipped with pressure transducers and a solenoid-operated valve, to allow oil into and out of the cylinder when extending or retracting. This is the hydraulic symbols legend taken from the schematics section of the DC scissor service manual. The hydraulic system utilizes one fixed displacement gear pump, and a number of directional valves for individual functions. The speed of the drive and lift functions are varied by the electric motor that drives the pump based on the operator's joystick command. Genie scissors descend by gravity when the down valve is activated, and the speed is controlled by a fixed orifice located in the lift cylinder port block. Here is the most common of the slab scissors hydraulic schematics. Displayed here, you see the hydraulic schematic and function manifold used on the GS 1530, 1532, 1930 and 1932. The pump assembly and reservoir are located at the bottom left of the schematic. To the right of the pump assembly you'll see the hydraulic oil return filter. All of the valves shown inside of the dashed box are physically located in the function manifold. Notice the additional dashed box inside of the manifold assembly. The additional dashed box is an indicator that the priority flow regulator and adjustable relief valve are, in fact, one single component. The lift cylinder, steer cylinder, brake release manifold, spring-applied brakes, accumulator and drive motors are shown at the top of the schematic. All of the hose connections are labeled on the schematic as they are next to the fittings on the function manifold. Shown here are the hydraulic schematic and function manifold used on the GS 2032, 2632, 3232, 2046, 2646, and 3246 models. The schematic and function manifold are very similar to that shown on the previous page for the smaller machines. On this schematic you'll see an additional lift cylinder with an incorporated relief valve, used during auxiliary lowering. Dashed lines are shown above the pump, continuing to a second page showing the outrigger system used solely on the GS 3232. The other difference is the addition of a 2-position, 4-way solenoid-operated valve, used to switch between high and low drive on all of these larger models. The following pages will utilize the schematic and manifold to outline, functionally, what happens when each function is selected. This page is designed to show a basic flow path for oil when the electric motor runs. This condition only exists for a moment under normal operation, before a directional valve is shifted to redirect the oil flow to the actuator for the function selected. The angled arrow through the electric motor symbol indicates that the motor speed is variable, or proportional. A fixed displacement gear pump is used, meaning the motor speed has to vary to provide proportional flow control for the lift and drive functions. Note that there is one single test port equipped with a quick disconnect fitting on these manifolds, used to connect an oil pressure gauge for diagnostics of all functions. As we view the schematics depicting individual functions, we'll highlight the components being used to perform the function, along with the component location on the function manifold. In this example, we've selected steer left. When steer is selected with the machine sitting static, the electric motor spins the pump at a fixed rate to provide enough oil to operate the function at 0.75 gallons per minute. Pump flow enters the function manifold at port P, and continues to pass through the lift drive select valve, labeled Y8. The oil reaches the combination priority flow regulator, relief valve, highlighted in green. The arrow perpendicular to the flow regulated port of the valve indicates that this valve is pressure compensated, with a maximum flow rating. 0.75 gallons per minute is allowed to pass through regulated port to the steer function directional valve. Any excess flow is forced through the secondary port, making it available for the drive function. In this case, static steer is selected, so the excess flow passes through the open port in the center of the drive function directional valve, and back to the reservoir. Solenoid Y3 or Y4 are energized when steer right or left are selected. With Y4 energized, the steer function directional valve shifts, connecting the pump flow to the barrel end of the steer cylinder. The right end of the cylinder is connected to the tank port of the valve, allowing oil to be exhausted, and return to the reservoir as the steer cylinder extends. If the steer function is held when the cylinder reaches end of stroke, the incorporated relief valve will open at 1,500 pounds per inch too, allowing the pump flow to continue downstream. This schematic shows the high drive function. In order to achieve high drive, the machine must be in the stowed position, with high drive selected at peak on. The pump motor speed is proportional to the position of the drive joystick, up to 4 gallons per minute. In the event of a deadhead situation, or a hydraulic system failure, the system relief valve, highlighted in purple, opens at 3,700 pounds per inch to protect the hydraulic components, and prevent a hose rupture. Oil passes through the lift drive select valve, continuing to the priority flow regulator for steer. 0.75 gallons per minute passes through the regulated port to ensure that steer is always available. Any flow exceeding 0.75 gallons per minute continues to the drive function directional valve, through the secondary port. If the steer function is not selected, 0.75 gallons per minute is allowed to pass through the tandem center port of the steer function directional valve, rejoining the flow from the secondary port, making 100% of the pump flow available for drive. Y5 or Y6 are energized to select forward or reverse drive. As the drive function directional valve is shifted, you'll see that pump flow is blocked, forcing the oil through a 50 pound per inch 2 relief valve, highlighted in green. This valve is in place to keep the brake release pressure 50 pounds per inch 2 higher than the drive pressure to prevent the brakes from dragging. With drive selected in the reverse direction, pump flow exits the function manifold on port M4, connecting to the right drive motor. In high drive mode, solenoid Y1 is not energized. Exhausted flow from the right motor continues directly into the left drive motor. This is called a series circuit. Exhausted flow from the left drive motor passes back through the drive function directional valve back to the reservoir. The spring-applied brakes are in parallel with the drive motors. As the drive system pressure increases, exceeding approximately 400 pounds per inch 2, the brakes release, allowing the drive motors to propel the machine. When the machine is driven downhill, the drive pressure is reduced significantly. This may cause the brakes to shudder. A nitrogen-charged accumulator is plumbed in parallel with the brakes, storing oil under pressure to prevent this from happening during a pressure drop condition. As the drive joystick is released, the drive solenoid is de-energized and the electric motor shuts off. The drive valve is allowed to return to the spring-centered position. The machine is no longer being propelled by the hydraulic system. Its momentum forces the motors to continue spin, in turn, forcing them to displace oil. The ports in the center position of the drive valve restrict the oil being displaced, as depicted by the orifice symbols, causing the drive motors to slow and act as service brakes. With the drive valve in the center position, oil escapes from the spring-applied brakes allowing them to set, acting as a parking brake. This series drive circuit is an effective way to achieve a high drive speed and traction, but does not provide the torque necessary for larger models to climb inclines for loading and unloading. This is because of a low-pressure differential across the first drive motor in the series. Generally speaking, if there is a low-pressure drop across the motor, it is doing little work. The following page will show the low drive, or high torque drive function. As low drive, or out of stowed drive is selected, solenoid Y1 is energized. The Y1 solenoid is shown at the bottom of the function manifold on the right. This valve is commonly referred to as the series, parallel valve. In a series circuit, we saw up to 4 gallons per minute entering the right drive motor. That meant that 4 gallons per minute was exhausted from the first drive motor to the second drive motor. When the series parallel valve is shifted, pump flow is exposed to both drive motors. If both tires maintain positive traction and the machine is driven in a straight line, theoretically they will each utilize half of the pump flow. The advantage of a parallel drive circuit is that there is a potential for a high pressure drop across both of the drive motors, resulting in higher torque. A parallel drive circuit effectively cuts drive speed in half, in comparison to a series circuit. The electronics further reduce the pump flow for low drive. A disadvantage to a parallel circuit appears if a tire loses traction. As pump flow is connected to both of the drive motors, the oil will follow the path of least resistance. The drive motor which has lost traction will receive all of the pump flow. High drive must be selected in order to recover from a loss of traction condition. When the lift function is selected, solenoid Y8, highlighted yellow, is energized, directing 100% of the pump flow to the lift cylinders. Pump flow is allowed to bypass the orifice restriction, and the holding position of valves Y7 and Y9. Vent hoses, drawn on this schematic with dashed blue lines, allow any fluid that may pass the piston seals to return to the reservoir. They also prevent vacuum while the linkage is being lowered. Y7 and Y9 hold the cylinders in position when the lift function is deselected. The adjustable lift relief valve, highlighted green, shows a pressure range from 1,800 to 3,700 pounds per inch 2 as this schematic is shared between many different models. The pressure necessary to lift the maximum rated load on a machine with 2 lift cylinders is significantly lower than the pressure necessary to lift the same load on a machine with 1 lift cylinder, due to the increased piston surface area. Note that the lift cylinder, labeled upper lift cylinder, specifies that it is only used in GS 3232 and 3246 models. Genie DC scissor lifts utilize a gravity down-lowering system. Y7 and Y9 are the solenoids used to activate the lowering valves located on the lift cylinder, or lift cylinders, under normal machine operation. In the de-energized, or spring return position, these valves are used as holding valves. When the down function is selected, the lowering valves open fully, allowing the oil to exhaust from the barrel end of the cylinders. Exhausted oil is metered out of the lift cylinder, as it is forced through a fixed orifice. The orifice size varies between different size machines. Once the oil passes the fixed orifice, it is allowed to pass back to the reservoir through the spring return position of the lift drive select valve. In the event of a battery, or control system failure, auxiliary lowering is required. An auxiliary lowering cable is connected to the manual override of the lower lift cylinder lowering valve. Pulling the red T handle, located on the drive chassis, opens the valve allowing oil to escape from the barrel end of the cylinder. On machines with 2 lift cylinders, the upper lift cylinder has an additional relief valve used for auxiliary lowering. As the manual override is activated for the bottom cylinder, the entire load of the linkage, platform, and its contents, is placed on the barrel end of the upper lift cylinder. With this pressure intensification, the relief valve opens allowing the linkage to drift down. It is common to have a small gap between the linkage after auxiliary lowering. Because of the linkage geometry, the pressure in the barrel end of the cylinder is reduced as the linkage approaches the stowed position. Manual brake release is available to move the machine, when it isn't able to move under its own power. The circuit on the left is shown as depicted in the hydraulic schematic. On the right, a black knob and red knob have been added for component identification. The hand pump symbol has also been changed to show an accurate depiction of how it works. To release the brakes, the black knob on the brake release valve is pressed in, preventing oil from escaping the brakes. As the red knob on the hand pump is pressed, oil is blocked from the reservoir, forcing it into the brakes. Releasing the red knob allows more oil to be drawn from the reservoir. Repeatedly pressing and releasing the hand pump forces more oil into the brake, acting against the brake piston. When approximately 400 pounds per inch 2 is applied, the brake piston overcomes the spring tension, freeing the friction discs allowing the shaft to spin freely. The following pages will show the outrigger hydraulic system used on the GS 3232 model. Shown for reference in the lower left corner, are the pump assembly and hydraulic reservoir from page 1 of the schematic. On the GS 3232, the outrigger manifold is in series with the function manifold. When functions other than outriggers are selected, pump flow passes through the tandem center position of the outrigger extend-retract valve into the function manifold. With this understanding, the pump assembly and reservoir will be removed in the following pages. The outrigger manifold houses a 3-position 4-way solenoid-operated valve used to direct pump flow to the barrel end or rod end of all 4 outrigger cylinders simultaneously. The outrigger cylinders have individual 2-position 2-way solenoid-operated valves in the barrel end. These valves are activated when the control system determines that the individual cylinder should extend or retract, providing individual outrigger cylinder control for auto-leveling. These valves serve as holding valves to support the load of the machine with the outriggers deployed. A pilot-to-open check valve is placed behind each of the holding valves as a redundant safety valve to prevent drifting and to meter the flow out of each cylinder when retract is operated. Each cylinder is also equipped with a pressure transducer, monitored by the control system to determine the position of each outrigger. Individual outrigger control operation is not available. The auto-leveling sequence will be defined in the following pages. The machine must be in the fully lowered position in order to extend or retract the outriggers. Lift is disabled through the auto-level cycle. When auto-leveling is operated with the outriggers fully retracted, solenoid Y40 is energized, directing pump flow to the barrel end of all 4 outrigger cylinders. Simultaneously, Y35 and Y36 are energized, allowing pump flow to extend the left front and right front outrigger cylinders. When the pressure transducers indicate that the front outriggers are touching the ground, Y35 and Y36 are de-energized. The front outriggers are deployed first, maintaining tire contact with the brake end of the machine to prevent runaway when setting the outriggers on an incline. Once the front outriggers are touching the ground, Y33 and Y34 are energized, allowing pump flow to extend the left rear and right rear outrigger cylinders. When the pressure transducers indicate that the rear outriggers are touching the ground, Y33 and Y34 are de-energized. When all 4 outriggers touch the ground, the ECU reduces the electric motor speed and provides individual outputs to level the machine in the front-to-back direction, based on the chassis tilt position, as indicated by the analog tilt level sensor Y-axis signal. Once the chassis is level in the Y direction, the ECU provides individual outputs to level the machine in the side-to-side direction based on the chassis tilt position, as indicated by the analog tilt level sensor X-axis signal. When the ECU determines that all 4 outriggers are touching the ground and the chassis is level, it will shut off the pump motor and sound an audible alarm, indicating that lift is enabled. As outrigger retract is operated, Y39 is energized, directing pump flow to the rod end of all 4 outrigger cylinders. The ECU provides outputs to energize Y33 and Y34 for 2,500 milliseconds. Pilot to open check valves meter the flow out of the barrel end of the cylinders, regulating the rate of speed that the chassis lowers. An orifice is located behind the pilot to open check valves to stabilize exhaust flow when retracting. After the rear outrigger cylinders have retracted for 2,500 milliseconds, Y35 and Y36 are energized, allowing all 4 cylinders to retract in parallel. When the pressure transducers indicate that all 4 outrigger cylinders are fully retracted, all outputs are shut off and an audible alarm sounds, indicating that lift is enabled.